Yes,
Yes.
sir.
Yeah. Last day I had sent you SVG image of the board that I worked with. So I hope you got it, right? Did you check it? Yes or no?
Yes, sir, we got it.
You got it. Yeah. So it's a copy of the whole board, right? Okay, let's start. So before I start, so today's topic of discussion will be push down automator, right? Today's topic of discussion will be push down automator, and the rule of thumb is whenever I talk about push down automator, by default I would be meaning non-deterministic PDS only. So whenever I talk about push down automata, quotes unquotes push down automata, I would be by default meaning non-deterministic push down automatas, unless otherwise stated. So whenever I would be talking about deterministic push down automatas, I will say deterministic push down automata. Whenever I talk about push down automata, it is by default. I would mean non-deterministic push down automata, right? So as you have seen in your finite automata case, here also we have uh, two specific cases of deterministic version and the non-deterministic version. And where did my board go? Yeah. So by push down automata, by default, I would be referring to non-deterministic push down automata. And whenever I would require to talk about deterministic push down automata, I will specifically say deterministic push down automata, right? Now let us come back to that language Venn diagram that I had already discussed in previous classes. But to classify push down automata and to fit it to the respective language class, revisiting the language Venn diagram is very important. So what about the language Venn diagram? We had regular languages, right? We had we had context free languages, right? We had decidable languages, and we had undecidable languages or Turing recognizable languages, right? And within this context free language space, I talked about three more classifications. Those are the unambiguous languages, and within unambiguous languages, I talked about the LRK languages, and within LRK languages, I talked about the LLK languages. Now, what I mean is, whenever I talk about, whenever I talk about um, uh, context-free languages, I would be talking about this whole domain, right? I would be talking about this whole domain. And as you had already seen, the machine equivalent of regular languages, this portion, the machine equivalent of this portion, the innermost core, the regular languages, the machine equivalent of this regular languages was the finite automata. That included both the DFAs and NFAs, both being of same capability as far as language acceptance is concerned, right? So the machine equivalent of context-free languages, we have a machine called push-down automata, right? I think I talked about this context-free languages. So remember, by this Venn diagram, context-free languages can be ambiguous. So this portion can be ambiguous languages, and only unambiguous portion is covered by this red circle. So context-free languages may be ambiguous. So I had given you questions also because I talked about this Venn diagram. So the machine that is completely equivalent to context-free languages is push-down automata, and by default I mean non-deterministic push-down automata, right? By default, I started the class with this default case. So this is where we would start, and informally we know that a push-down automata is capable of accepting context-free languages, right? And we started with the classic example of the language of 0 and 1 n greater than equal to 0. And what are the salient points? This is not regular, that you know. This is not regular. And by now, by the grammar definition, by the CFG grammar definition, you also know that this language is a context-free language, right? Now today, so this language being a context-free language, what does it mean? It means that if this is the language 0 and 2 n, if this is a set that contains strings, same number of strings with same number of zeros and ones, this can be generated by a CFG, and this may be accepted by a machine called a push-down automata. And we saw how a push-down automata, a machine called a push-down automata, can be used to accept this language, right? And since this language is not regular, a finite state machine was incapable of accepting this language. And we argued that we need a stack to accept this language, a stack so that the count of zeros and ones can be taken. So in essentially, a push-down automata is nothing but a finite automata. It's a finite control program. A finite automata, that means a finite control with an input string. This is the input string. A finite control with the input string, as well as you have a stack. That is how we define a machine to accept this language. I hope you remember. And this machine is nothing but the push-down automata. By default, it is a non-deterministic push-down automata. So now I am not going to differentiate between deterministic and non-deterministic when I will be defining this machine um, as a whole in a very simpler form, right? So there is a finite control, and as usual, so this is a finite control, and for this portion was for the finite state machine, finite automata. This portion was, if I talk about only the input and the finite control, it's a finite state machine, right? FSM. And when I add the stack, when I use the power of stacking, when I use the power of memory, then I call that this whole machine is a finite state automation plus a stack plus the controls that you need to control both the input and the stack together, right? So if I say that okay, this is finite state machine plus a stack. Now how do I define it? Any idea? How do I define it? So the finite state machine was a 5 tuple. It had Q, sigma, del, Q0 and F, right? Now what we can do is very simply, okay, so this was the finite state machine 5 tuple. I hope you remember, where del was defined as Q cross sigma taking you to Q. So if it is the non-deterministic case, if it was the non-deterministic finite automata, it was Q cross sigma taking you to 2 to the power Q, right? So if I want to add the stack element here, very simply, what I will do is I will define the PDA based on the definition of FSM as a 6 tuple Q sigma. I will define a separate stack alphabet that includes the the the, the alphabet sigma, and you are done, right? So in the finite push down automata case also, you have a final state. You can have many final states, but that can be equivalently talked about a single final state by epsilon transitions. I will show you how. And what we have done is with the finite state machine 5 tuple definition, I have just added the stack alphabet. So this is an addition to the finite state machine tuple, and it is called the stack alphabet. right? Now, what is the stack alphabet? Now, stack alphabet is nothing but your 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 main alphabet of the symbols plus something more. For example, you may require a special symbol dollar to mark the end of stack, right? That would be important when you design algorithms. So that so if I only have a dollar to indicate the end of stack, at that point of time, tau may be called as it contains 0 1 from this sigma. Sigma was 0 1, for example, and it contains a special symbol called dollar. So tau is we define tau is a stack alphabet. That means only these symbols. So if tau is 0 1 and dollar, then we say that okay, uh, these are allowed to be pushed on stack. That is what I mean. So you can push a 0, you can push a 1, you can push a dollar, you can pop a 0, you can pop a 1, right? Popping a dollar doesn't have any cognitive value, it doesn't have a meaning. So see, if your concepts are clear, the definition of a PDA becomes extremely clear, right? So we argued in some previous classes that a finite state machine, since it doesn't have memory, it was incapable. The finite state machine alone was incapable of dealing with 0 and 1, and because we need to count. So we added a step. So that much we have done. We have added a stack. So if it is that we have added a stack and we have added some controls, so it should mean that okay, we have added a stack in the tuple definition, and we should be adding the controls to control both the stack and the input symbol. So the idea was looking at the input. So the idea was if your input head is here, you look at the input and you look at the top of the stack, and then you decide what to do. For example, you are in some state Q, you look at the input symbol A, and you look on the top of the stack as B, and now together you design. If you are in Q, if the input is A and if the top of stack is B, then you may go to P. Got my point? And you may go to P and some state P by pushing some symbol on the stack, by either a push operation on the stack or a pop operation on the stack. These are the only two operations that you are allowed. So you can write that I can go to some state P with some remaining gamma on my stack. So this defines a transition of your PDA. Is it clear? So that becomes so simple. So let us write del. So del of this PDA looks like it was Q cross sigma in case of finite state machine, and now I write Q cross sigma cross tau because I take into account the top of the stack. I should facilitate a movement by seeing both the input and the top of the stack. So I should be seeing both the top of the stack and the input, and then decide that okay, I'm in Q, I should be moving to P, and after moving to P, I should be popping and pushing some elements on the stack, right? So how to define del? So it's del can be defined very simply. 1 minute, my board has just stopped responding. Yeah. So how to define del? I should define del as it takes Q cross sigma cross tau to the power set of say Q cross tau, right? That means I am in some state Q. I see a symbol A in the input, and there is a top of stack. On the stack, a del of this should be I should be going to a set of states, right? By P, I'm in the power set because by default I am defining by PDA a non-deterministic push down automator, right? PDA. So I talk about the power set immediately. So it may be that I go to some state P and I push some symbol on the stack. So it means that okay, I pop the top of stack and I push a B. This is the meaning, right? This is how I go. There may be a finite number of such states. This is finite, remember. So that completes the definition of a push down automator, right? Now this definition is this definition accompanies with something that you should conceptualize, that what are the stack operations. Let me write it down. Stack operations. What are the stack operations? The stack operations can be categorized into two categories. One is read and pop, read plus pop together, right? Or ignore. can also ignore. You can read or pop, read and then pop a symbol from the stack, or you can ignore the whole process, or you can push a symbol on the stack, or you can ignore. Right? So as I say that I can ignore, it means that I will be pulling the case of epsilon here also, right? So and this stack operation is defined on the stack alphabet tau, and that is nothing but sigma union some special symbols that you may be required to use when you use the stack for your algorithmic purposes, right? So tau is nothing but sigma union special symbols. So what I mean by this is the stack alphabet means the means the symbols that you can push and pop to and from the stack. That is what I mean. I don't know why my board is stopping response at times. Just give me 1 second. Are things clear? Yes, nobody responding.
It is
Hello.
clear, but it's like fadey, sir.
Yeah,
Like it's
it's
not
there,
that
but
clear, sir. Like
it's
it's
not
not
that
dark.
clear. Okay, it's not that clear. Can you say why? Can you ask me questions? I would be very happy if you ask me questions. Why it is not clear? Please, please.
So maybe your screen brightness, or maybe like the pen you choose is the tip of the pen you chose in the marker is too thin.
Is it? But I am
Yes.
using a different software. I'm not using Miro.
So you can use a thicker like a pen, a thicker marker
This
here.
is the yeah. This is the thickest, I think. Altogether,
That is
it
the
has
thickest.
stopped responding. Give me 1 minute.
Okay, sir.
I restarted my app. Now, can you see now?
Yes, sir. Now it's clear.
Now it's clear.
Yes, sir.
Okay. So I was saying, what are the stack operations that that you are allowed to do? One is very obvious: read and pop. You can read a top of stack and pop that element, or ignore the whole operation altogether, right? Or this was one operation. The second operation that you are allowed to do is push a symbol on top of stack and or ignore, right? So what I mean by stack alphabet is the symbols that can be read from the stack, popped from the stack, or that can be pushed onto the stack, right? Those are the symbols that sigma already has, the symbols on which the string should be built. Union some special symbols like you define a special symbol with dollar to indicate uh, the bottom of stack, right? Because that would be important if you write conditional statements in your programs. Is it clear? Now this was the machine design part. Now what I would like to convey is, so so we saw how a finite state machine plus stack gives you a PDA. Now this is evident, right? How a finite state machine plus stack gives you a PDA, and adding this stack gives you the extra advantage of counting, right? And once you are allowed to count, you can accept, you can check on whether such strings belong to your language or not, right? Same number of zeros and ones. Fine. Now, since so previously what I talked about was the machine part of the definition. So for the finite state machine part, how do you show transitions graphically? How do you show transitions graphically? So you are in a state, you get a symbol A, and you change state. That is how we show in case of a finite state machine. Do you agree? Do you remember? So you are in some state, you get a symbol and you change state. That is what you do. So what should be the case when I join this finite state machine with a stack to make a PDA? So what should be the transitions graphically? The transitions should be very simple. See, you are in some state and you change the state. You are in some state Q and you change state to P. In case of a finite state machine, you got a single symbol and you change it to P. This is known to all of you. Now what I say is, now that I have added a stack, I got a PDA, and how to represent a PDA graphically. I am in some state Q. I would change state to P, right? If I have A as the input symbol, right? If I have B as a symbol on the top of the stack, and if C is the symbol that is pushed on the stack. So what does A mean? A means current input. What does B mean? Current top of the stack. And what does C mean? Push this symbol onto the stack. So B is the current top of the stack and pop it. So if A, so what I mean is if A is the current input symbol on the input tape, I give a comma. Then I say if B is the top of the stack, and if it is the case that you are required to pop B and push a C, only then you change a state from Q to P. So this is the diagrammatic picturization of a PDA move. Does it make sense? Yes or no?
Yes, sir.
Yes. Now I would like to allow B and C to be both epsilons also. B and C to be both epsilons also. What does that mean? So when B is epsilon, it means stack is neither read nor popped. Remember, this is B. B is the current top of the stack. So if I write something like A comma epsilon goes to epsilon, it means that A is the current symbol in the input on the input tape. By epsilon, I mean that the stack is neither read nor popped. I do not read the stack and I do not pop the stack. And here an epsilon means that nothing is pushed on the stack. So to include epsilon in whatever you do, you should be including epsilon everywhere, right? So I include epsilon in A also. I allow epsilon to be present in A. So once I say epsilon to be present in A, what does it mean? That the input may be empty. That is what I mean. So to allow epsilon everywhere, so essentially B and C are members of the stack alphabet, right? C is the symbol that needs to be pushed on the stack, and B is the symbol that needs to be popped, read and popped from the stack. So B and C are from the stack alphabet, and A is an input alphabet, symbol from the input alphabet. So what I mean is, in this definition, to make the definition more proper and inclusive, again my board has stopped. I don't know what is happening. 1 minute. So here, come here. So here, what I would do is I would say that Q cross C. This was the definition of the PDA, right? This was the definition of PDA. So if I want to include epsilon to be dealt with as an eligible symbol for transition, I would write to give it a more proper form Q cross sigma star, not only sigma. It would be Q cross sigma star, and you can write tau epsilon because tau star doesn't have a proper interpretation. It means that sigma star means that you can, okay, let us not write sigma star. Let us write something like it would be sigma epsilon. So that gives you a more robust definition of uh, the PDA if I want to include epsilon in my consideration, right? So what I say is I am in a state Q. I see A as the current input symbol. I see B as the top of the stack and I pop it. And then I push C on the top of the stack. And only then I change my state from Q to P. Is this clear? So what I mean is, if I want to include epsilon interpretations everywhere in A and in B's and C's, what I mean is A is always an element of sigma, and B and C's are elements of tau, right? Because B is the top of the stack that is being read and popped, and C is the symbol that is being pushed on the stack. So B and C together with A gives you the unified control of both the input alphabet and the stack alphabet, right? So B and C are legitimate symbols that can be pushed on the stack, and A is the legitimate symbol that can be read from the input alphabet. So if I want to include epsilon everywhere, so what would I say is, other than sigma, I would write sigma epsilon, and other than tau, I would write tau epsilon. Now, what is sigma epsilon? Sigma epsilon is nothing but sigma union epsilon. I want to consider epsilon in my input alphabet. And what is tau epsilon? Tau epsilon is similarly nothing but tau union epsilon. So only when I define sigma epsilon and tau epsilon, my del immediately becomes Q cross sigma epsilon cross tau epsilon going to the power set of, without writing power set, I can directly write 2 to the power uh, Q, that means I change state, cross sigma, right? Right? 2 to the power Q cross sigma. So this is how I can Q cross sigma epsilon. So this is how I can represent the PDA transition. If you remember, the transition for an epsilon NFA was Q cross sigma star taking you to 2 to the power Q. Do you remember? This was epsilon NFA, most general definition of epsilon NFA in a finite automata class. And this is the most general expression of non-deterministic push-down automata. So as I promised, I will be leaving you today. If you have questions, write down whatever you have in your mind. You can ask me in the next class, and you may get ready for your exam. Okay, that ends today's class. Okay, you have any questions, you can ask me in 5 minutes. Yes, any questions?
No, sir.
Okay, so do you wish to have 5 more minutes, or do you wish to leave and prepare for the exam?
We can.
So I think you are
Yeah,
prepared, sir. So it will
prepare
be
for the
better
exam.
if we leave now. Yes, sir.
Yeah. So see, how I perceive things is I don't like forcing people in my class, because you would be in my class listening to me and thinking of your exam, right? That has absolutely no meaning. So it is, if you tell me that I can take 10 more minutes, you have to promise me that you would be very fresh and listening to me with 100% concentration. But if you say that, okay, uh, I am in class, but I'm thinking of the exam, so it is better to leave the class. What should I do?
Sir, it's fine till 4:30, sir.
Okay, okay. So let us take an example. So let me go by the version of the CR. So let us take an example, and with this pictorial representation, so we have seen how. So up to these things are pretty clear, right? So I'm trying to explain things in a very simple way. So as far as the visualization of the stack and the machine was concerned, 0 and 1 and was pretty easily understood by you, how we can use a stack to count the ones with respect to the zeros that we have seen. Now I want to give a pictorial representation of the 0 and 1 in case, and you would be so happy to see. For example, say I start in a state A, right? I am in a state A, and what is the language that I'm going to accept? I am going to accept 0 and 1n, n greater than equal to 0. So this is the language I'm going to accept with a PDA, or putting otherwise, what you can say is we are going to design a PDA that should accept this language. So what is a PDA? A PDA is a finite state machine with a stack, and a PDA is a machine whose transition is defined like this, right? In the most general case, a non-deterministic one, where we allow everything on epsilon. So I start in a state A, and I will go to a state B. In what condition? We have to check. So internally, you should be framing what your operations should look like in the machine equivalent part, right? So let me divide the board in these two portions so that you can see what actually we are doing with this pictorial representation. So I am in some state A, and in that state, what are the options? In that state, if I see a epsilon, that means the input is empty and the stack is empty, both epsilon. What I will do? I will push a dollar the stack. This board is disturbing so much. Just give me 1 minute. It again stopped working. Let me go back to my row. Okay. So this is the language. Is it visible? I think it's
No,
not
sir,
visible, right? Yeah,
it's not
it's not
visible, sir.
visible. Yeah, yeah,
It's like some scratches on white screen.
yeah, yeah, yeah. So what to do? Just hold on for some time. I don't know what to do. 1 minute. I've changed the nib of my pencil. Let us check if it works. So I've come back to this board. Sorry for the interruption. Yeah, so we have come back. So what is the first case that you can have? The first case is that that both the input and the stack are empty, right? So if both the input and the stack are empty, then you intend to push a dollar, right? So epsilon comma epsilon dollar. So is this clear? So if you are seeing that the input is empty, see I'm drawing here. If you are seeing that the input is empty, that means you have an epsilon, and the stack is also empty. To start operations, the stack is also empty, for example. So if the stack is at all empty, I should not be drawing all this. Rather, I should be drawing an empty stack, something like this. The stack is empty, right? So you see an epsilon. So the finite control says, so this is a finite control. It says that if the stack is also empty and we have not yet started seeing the input. So this is the input, for example, A, B, C. Okay, let write the input in terms of zeros and ones because I'm considering 0 and 1 in language. So let me consider zeros and ones. For example, the string is 0011. You have to check, you have to build a PDF of this 0011. So at the very first case, when we have not yet started to scan the input, we have epsilon here and we have epsilon here. So what to do? You pop this epsilon and push a dollar, so that you are ready to start your proceedings. This is what I mean. And you change a state to B. In B, you are internally coding the function of state B as you take zeros as long as you can. So you move right, you see the zeros. As long as you see the zeros, you you go on pushing the zeros on the stack and remain in state B. That is what we have conceived, right? So if you see a zero and if you see an epsilon, that means the position just above the dollar is epsilon. That means the stack is not having any zeros or ones. So once you have pushed the dollar sign, now the pointer is here, right? It is empty. So once you see a zero, and you see an epsilon here, what you do is you push a zero. So if you have an epsilon, you see a zero, you push this zero, right? And do as long as you see a zero and remain in B. Does it make sense? Yes. Now once you are in B, what you do is see the non-deterministic part. You can move to C. Doing nothing, right? So if you have exhausted seeing the zeros, you can just move to a state where will consider popping those zeros and pushing these ones, and that state is C. So to facilitate this epsilon transition from B to C, that means doing nothing, I would rather write epsilon, comma epsilon, arrow epsilon. Does it make sense? So it's just like an epsilon transition of an epsilon NFA, if you can visualize. So I go to C, and in C, what I will do is, if I see a 1 and a 0 on the top of the stack, if I see a 1 in the input alphabet and a 0 on the top of the stack, I pop the 0, right? And I continue doing this unless and until I find an epsilon at the end, and together seeing an epsilon at the end means the input has exhausted. And if the input was the correct input, that is 0 and 1 n, it by exhausting the input, it means all the poppings is being complete and the dollar should be exposed. So it means that epsilon is, we have achieved an epsilon in the input and we have seen a dollar on the stack, and what we do is we do nothing and we accept at D. Does it make sense? Is it the same thing that we are talking about? Yes? Anyone? Yes, Basu? Is it clear?
Yes, sir. Yes, sir.
Yeah. So it is clear, right? So it's so easy to visualize. So if you go back to 2 to 3 classes, you know how to visualize this operation. And now I have just converted this operation in a formal domain and defined in terms of a machine. This is what I have done. I have not done anything else, right? So I think I should end here, right? Okay. So if you have any questions, you just note down the questions so that you can ask me in the next class. The next class will be on Thursday, and I hope to get more time on Thursday, right, Basu? you don't have an exam on Thursday. Yes?
Yes, sir.
Yeah. So Thursday I'll be taking classes from 4:30. Okay? Okay.
Thank you, sir.
Yeah. Bye.
Thank you, sir.
Thank you, sir.